Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of cyber physical systems. So today we will be starting with our coverage here on quadratic program based safe control design. So before going into any of this, let's first understand that what we mean by all this. So we have talked about some methods of controller design, and that was the pole placement based method. And let's also appreciate that there can be several other methods of control design, and one of them is designing optimal controllers. So what that would really mean is that you have a cost function which captures your control objective, and the cost function can be expressed in several ways. One of the ways is a quadratic program, and we will see what such programs mean. And so essentially the controller design boils down to solving that optimality condition or that objective function, or basically maximizing or minimizing that objective function at every instance of the control iteration. So we set up a cost function which captures the control objective, and we figure out what should be the control input so that this cost function is optimized in that control iteration. So that's the basic idea of designing such controllers, and we will talk about one such class of system called linear quadratic regulators. So we start with a system assumption. So you have let this be the system assumption here, okay, where you have A and B. In general, they can be like time varying matrices, okay, like we discussed earlier at the start of our course. And VC is a process noise with a mean value that is 0, right. And if you can also sample the system, and if you sample the system, you will typically get a difference equation like this, where the time instants are given like this, right. The T is equal to kh, and then so at different such time instances, so you have let me just figure this thing in a better way. So let us say x at k plus 1 h will relate how to the values of phi and gamma at k h. So that is what we are trying to talk about here, okay. So this is y, and this is a y equation, okay. Now this V is your process noise and E is your measurement noise here. And for both we will assume that they are Gaussian noises with 0 mean, okay. And we will have these usual relations between phi and A and gamma and phi, etc., right. And also what we will assume is well, how do I parameterize these noise signals? We will parameterize them as 0 mean Gaussian white noise processes for which the mean is 0, and their variance is given by R1 here for the process noise, okay, expectation of this and the variance of the measurement noise is R2, and the covariance of variance and of the measurement and process noise together is R12. So these are the terminologies we will be using in this control design objective here, okay. Now let us understand what is a linear quadratic regulator. Like I said, the general class of controllers we are talking about here is there must be a cost function which will kind of capture the system's control objective, and in every iteration the choice of control input is with the objective that you want to optimize this cost function, and this thing will go on in every iteration of the system. So the way we look at optimizing the control here is that we have a linear system, and for that the state needs to be stable. That means it should be hovering around an equilibrium point, which is the current operating inside the current operating region, and so x should not deviate too much, okay. Assuming in general that this deviation is non null, it should not deviate too much, right, and you are operating around an equilibrium of 0, okay. So That means the value of x can be a bit above or below 0. So, it can be positive and negative both. So, I would like to minimize its squared sum, right, so that is the idea. Also, for health of the control system and for many practical considerations, I won't like the control input to be changing drastically, because no physical system likes drastic changes, right. There are inertial constraints, there are also constraints like actuator saturation and stuff. So, all you want is that the system must steer in its trajectory very smoothly, and it should not veer too much around the set point, and the control input should not be changing in a very ad hoc drastic manner. Okay. So, that change should also be smooth, right. So, the way to encapsulate these ideas in a nice cost function can be as follows, that well, you have something like this, which is capturing that well, what is the value of this state, is it deviating too much? If it is deviating too much, then the value will be high or low, too low, below, I mean in a negative sense. So, well, why not take a squared sum like this, because in a way, as we have seen while we studied about Lyapunov and all that, we have seen that well, something like this, a quadratic form of x is also in a way denoting the energy stored in the system, right, and the system in its stable state will like to be steered towards its lower energy states. So, in general, if the state vector has multiple states, then their contribution to this energy indicator can be different, right. So, ideally we will like to have this in a nice quadratic form like this. So, it is not just x square, but rather you have x transpose x with a weight matrix in between Q and C, and what is the coefficients of the weight matrix doing? It is assigning, let us say, more weight to some variable x which is more sensitive, less weight to some variable which is less sensitive, something like that, right. So, that is, and it will be a symmetric positive definite matrix. So, that is how we actually define a cost function which is going to capture this thing, that well, x must not be varying too much from the target equilibrium location. Okay. Now, like I said that I will also like to have the control input not changing drastically. So, we can introduce a similar quadratic term in my control input for my control input, and once I do that, then I will have this weighted quadratic term for x, and I would also have a weighted quadratic term for the controller for the control input, right. And overall we will like to minimize a lost function which is kind of looking like this. So, here as you can see you have considered x, you have considered u also, and here you also have a weight matrix which is capturing x and u together here. Okay. And not only that, I will like to also consider that well, what is my state at the end of this control window. So, we are actually when we are trying to take it as a summation, we are considering not only at single instances, but the cost function has to be kind of windowed, because we are trying to see that well, suppose I am trying to choose the control input right now, but I am not only worried about what will be the effect of this control input at this kth time instant or in this interval of k to k plus 1, but what is the effect in the long run up to some finite horizon of size n. That means, I want to capture mathematically that well, how do I choose this u so that this cost function is optimized not only in this period, but over a finite horizon. That means, let us say over the next n successive periods. I want to know about that. So, that is why n comes as a parameter in this design. You can choose n to be 1, 2, 3. The more is the value of n, if you think what you are doing is you are unrolling your loop over n future iterations, so that your current choice of u is more and more knowledgeable. Because if you use a smaller iteration, a smaller n, that means you are not really looking ahead into how the system will unfold based on your input now, right. The more you choose a higher value of n, you are unfolding the system for a larger horizon, and then you are really able to calculate that what is the effect of my system not only in the next time step, what is the effect of my current control input not only in the next time step, but the next to next, the even further, and all these time steps. Okay. So, based on that you choose a suitable horizon n for doing this integration, and you assume these quadratic terms which capture the interaction of x, u and x and u together here. Okay. And last but not the least, as I also said, that you also want to know that at the end of the horizon what is the final value of x. So, for that you end this additional term here for this nth step. And since after the nth step I am not considering the control any further, so that is why I do not have a control term in the nth step, but only the final state, because I am interested in this, that currently I given you what really does my state become through this evaluation and finally into the nth step. So, that is why you see this integration is covering this much, and additionally you have this term here for the nth step. So, if you write this thing in kind of a shorthand, it will be like this, where you consider x and u together as a vector, okay, and you can have you can have this integral over 0 to this horizon n, and you have the state with x and u here, and so basically you have a full quadratic expression on both x and u together. So, x transpose u transpose here and x u here, like that. Okay. And not only that, the way we are writing it is in a nice manner. We are trying to capture all these things together, these four of them, okay, using QC, which should be this. All of these individual coefficients are symmetric, and QC is the weight matrix. So, all we are doing is we are writing this expression together in this nice form here. Now, the question is, well, we said that we will integrate and all that, but what are we really trying to look at? So, we are trying to look at what is the average cost of this summation. So, we bring in an expectation here. Now, what we will try to do is we will try to minimize the expected value of this objective function. Okay. So, that is why we say that the objective here is to design suitable optimal control signals that minimize this loss function, and the loss function is nothing but expectation of this integral 0 to nh, this analytical form that we have. Okay. Now, since this is a quadratic form, j will have a parabolic function if we consider it in the space of x and u, because you see that it is a function of both x and u. This is the state, right. You have a quadratic form which is x transpose q x, where x is x u, right. So, this is like a, if I plot it in a state space, it will be a parabolic function. Now, since this will be a parabolic function, it will have a global minima. I hope this is clear. Every parabola has a lowest dip, right, and that is the global minima which we intend to find as part of this optimal control problem. We want to figure out that, well, what is the control input values for which this function will reach the global minima, and then that means if I choose those values, then for that we will actually have the system in its least energy state with the smoothest possible trajectory and the smallest possible control inputs. So, let us get about this in the discrete domain. So, what we will do is in the discrete domain we will change the integral to a summation, and we are assuming the periodic sampling with h as a sampling period in a discretized version. So, this entire thing will now look like this. Okay. So, what is j is basically you are starting from k equal to 0 to n minus 1 and you are summing it over this, right, this j k, where j k is this integral in a single step, okay, and plus the last state, this one that we talked about here. Okay. So, let us first understand what just happened. So, we said that well we will evaluate it in the discrete domain. So, in the discrete domain, that would really mean that I am going to sum up all these terms. So, that means I do not integrate the full thing from 0 to n h, but rather I consider these small integrals in each of these sampling periods, right, because this is discretized with an h sampling period. So, consider these integrals in each of these sampling periods with these following terms like we already discussed, right, and then that is your j k, that means the value of j in the kth instant. Now, you are going to sum it over from 0 to n minus 1, because essentially you are looking for the summation from 0 to n h, right. So, all you are doing is you are looking to integrate over a continuous period from 0 to n h. Now, you say that well you break it into these spaces of h, figure out these integrals in individual points. So, those are your values of j at k, k plus 1, k plus 2 up to k plus n minus 1, right. So, that is why you do summation from k equal to 0 to n minus 1, and for each of these intervals you have these interval integrals from k h to k plus 1 h. In this interval the integral value is j k. From k plus 1 h to k plus 2 h the value is j k plus 1. So, like that. And of course, we know that if I do this integral you will get something in a nice discretized form. So, whatever we get that is what will come here, okay. And then there is the final step. So, then from just we do these integrations, we come from the discrete continuous domain to the discrete domain. So, whatever weight matrices we started with in the continuous domain, they will now get converted into the discrete domain variants following these integrals. So, I hope this is clear. So, this was my continuous domain weight matrix. Now, if we apply this integral, this is how they will change, and here this phi, gamma, they are the usual symbols that we use for the systems matrices when we transmit when we convert them from the continuous domain to the discrete domain. So, yeah, so this is phi 1. Here we, as you can see, that we are saying j k is this, which will be equal to, I mean, will the integration done, it should be this I mean weight matrix over weight matrix is q 1 with its weighting x, and weight matrix q 1 2 in the discrete domain, it is again weighting x and u, and weight matrix q 2 is weighting q, right, it is weighting u. And what is q 1, q 2, and so this is your discrete domain version of q 1 c. Here this is your discrete domain version of this weights here, right, and you also have this q 2 here. So, let us understand, of course, this conversion can be easily done through some standard tools that we have, and once this is done, what is the idea is when we are doing this optimization in the discrete domain, then just like our older control designs, what will happen is this u is going to be constant here over these intervals, right. So, I can just free the u here, right, when I am doing the integration inside this interval, right. So, my expectation will just have a formulation like this. I mean, I can just write this value of u as fixed to be u k h. So, this would be u transpose k h, sorry, that is already here, and it is in this form, right, where we have already figured out that well in the discrete domain what should be the value of these individual weight matrices using this kind of expressions that we have here. So, just looking back, so we started with this we started with this overall integral, and then we said that we are doing it in a discrete space. So, I will have samplings at every h point, right, h sample after each period. So, at each of these intervals, the value of j can be found by integrating inside those sampling intervals. So, it should be this, and then once you find the values of j or some form representing the value of j, you put them in this summation. So, that is the idea, and you can figure out from this to this how we come by converting this from q1 c to q1 using these equations that we have just written. So, we are not going into how this will come. I think you can actually figure that out based on our previous coverages. So, in overall, let us focus here, because these things can be done, we can actually figure out them, or even better, let us think, I mean, if you feel overwhelmed by all this continuous time to discrete conversion, let us think that, well, you are given the system in the discrete domain directly. Okay. So, then you are starting your cost function design right from here. Okay. So, you have the loss function designed here, and you have this state space formulation, where with x and u, you have a quadratic form over which you have a summation, and you also have the final state n for which you have this. Yeah. So, note that this summation is only over the first term, and at the end you add one term for the final values of x and u at the nth step horizon. Okay. So, this is your final j. Now, the objective is that, well, I want to find out what would be these control values at each of these iterations in the horizon, so that this function is minimized. Okay. Now, this is a deterministic system we are considering with this value of noises Vk and Ek as 0 here. Okay. So, we are making it simple. We are considering that, well, the system is simply evolving following this equation. So, the noise terms are all 0, and my objective here is that I want to determine what is this control sequence. So, what I mean by this is, let us say what we are really doing. So, let us say this is k, this is k plus 1, this is k plus n. So, I am looking at how the cost function will change over this entire interval up to this n horizon, and there will be n positions where these control updates will be given, right, from u0 to un minus 1 here, right. So, in this cost function, you see there are those n unknowns. I mean, what should be the value of u0, u1, u2, etc., and eventually I will get to some state here. The point is, how do I choose these values so that this overall cost function is minimized, right. So, if I am somehow magically able to solve this, then I get a sequence of control inputs. If I apply them starting from here, I will minimize them. So, that is how this optimization works. That means, I will solve this online, and I will generate u0 to un minus 1. Among them, I will apply u0, because that is the control input relevant now, and then the system will evolve. Okay. So, once the system evolves and I come from k to k plus 1, now again I have measurements of x. So, again, so this was my k plus n, and then here I have my k plus n plus 1. So, when I come here, do I apply? So, I computed u0, u1, etc., right, up to un minus 1. Now, what do I do at k plus 1? Do I apply the old u1? No. Again, I will form another cost function with the horizon n. That means, it will now be from k plus 1 to k plus n plus 1. Okay. And now, I will again compute a set of new control inputs u1 prime, u2 prime, etc., up to this horizon, and I will apply the first of them right here. So, see, this is like a rolling optimization. You figure out n inputs, but you only use the first of them, because that is what you should apply now. You could have used the second one in the next step, third one in the next step, but then why don't I really do it? The reason is those values are like already stale, in the sense those values have been computed assuming that you have measurement of the current state, whereas in the k plus 1 step you will receive a new measurement of y, right, a new measurement of x we are assuming here. So, you will receive a new measurement of state for the system. So, then instead of again applying u1 and u2 and u3 like that in the k plus 1th state, with the new measurement you will create the optimization problem, and you will again create a sequence of control inputs, and you will apply the first of them. Of course, we are assuming that you have enough processor bandwidth available to do this, and we will work like that. So, that is the idea here. Now, the question is that, well, how do I really go about solving this problem? The idea here is that while minimizing this function, we will use some principles of optimality and dynamic programming. Now, what this really states is that whatever is an optimal policy that I choose as an optimal property right now is that, I mean, I would say that this policy is optimal in case whatever is my initial state and my decision that has been taken, it must be optimal with respect to the state resulting from the first decision. So, let's understand what it really means. So, let me just write this down. So, the idea is this, that I say that this is the principle of optimality, we have spoken and we have written it down. So, it means that, well, you have a sequence of decisions to take, right. Now, I would say that, well, the first decision that you take in this chain of decisions I will say that it is optimal if, due to the decision wherever your system lands up to, the remaining decisions will also be optimal from this state where you have landed with the first decision. That means, the first decision that I took, that means the first control action that I took was not optimal only for that time point, it was optimal for all future time points also. That means, it is not that due to that control action the loss function got minimized only in that interval, and had I not taken that action and I have taken something else, then it would have facilitated future actions, and because a different choice of this current action could have made made a choice of future actions possible, so that the overall loss would have been minimized. That is not the case. This is what is optimality. It means that whatever I choose now is something that based on that, wherever I land up, from that position, whatever are my future actions, those are also optimal. Okay? Let's again understand that whatever I choose now as an action is not only optimal for this interval, it is also optimal for future intervals. That means, for this choice that I made now, there exist choices in future, and once I make those choices along with this choice is the best possible way to minimize this function. Okay? I hope this is clear now. Now, why does this principle of optimality comes in play here? Because we will try to use this to figure out that, well, how to solve this problem and how to solve this idea of computing u here. So, what we will do is we will assume that initial decisions may have been optimal, right, and based that helps us to do one thing, that helps us to start computing the control input for future, that means from the nth step, and then going back in time towards the first decision. Okay. So, because we will assume that in this case we are going to compute the u sequence in such a way that they are all optimal. Okay. That is why it will be possible, that is why we will take this strategy that we will compute the action at the last one, and then we will roll back in time to compute the previous actions. So, that is the point we wanted to make, that it is possible to determine the best input in the last step independent of how the previous choices were made, because we are always assuming that those choices are all optimal. Okay? And those along with whatever optimal choice we make here are together optimally reducing the loss function. So, that is what we will do. So, fine, we will conclude our discussion today here, and we will resume from this point in the next lecture.